Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello, dear students. Welcome again to this TV learning program. I'm teacher Pascal. Today I will be with Senior 4 students learning a lesson of unit number 6. The unit is Trends in Chemical Properties of Group 1 Elements and Their Compounds. And in the previous lessons, we discussed the physical properties and the reactivity, but today we will focus on the chemical reactions. We have seen that the reactivity of metals, including group 1 metals, the alkali metals, it increases as we move down the group. And I hope you remember the reason. It's because the atomic radius increases and the ionization energy required to lose an electron, it decreases. So it becomes easier for the atom to react. And after that, we have to go deeper and see some of the reactions that these metals can undergo. And before we look at the various reactions, let us read the objectives so that you can know what you should be able to do at the end of this lesson. You should be able to describe the reaction of alkali metals with oxygen, reaction with water, reaction with dilute acids, and why not the concentrated acids, and halogens and hydrogen. But with the concentrated acids, it's not something you can do in a school laboratory, because it is very dangerous. And number 2, you should be able to describe some properties of some compounds of the alkali metals. We will have a look at the properties of some compounds of these alkali metals, but not all of them. To mean that we will have another lesson on the physical and chemical properties of the compounds of these alkali metals. Reactions of alkali metals. Do you remember what we used to show that the reactivity increases as we move down the group? We used a reaction, and that was a practical. We used a reaction of magnesium with water as well as that of calcium with water. We saw that calcium is more reactive than magnesium. And we said it is the same with group 1 metals. You remember the video we used to demonstrate how the reactivity increases as you move down the group. We showed that when these metals are put in water, they react with water. If you remember, there is something which looked like a smoke which was produced. And it shows the products, or that is one of the products we form when these metals react with water. You remember the air bubbles which were produced when calcium was reacting with water. It's because of the gas, the gaseous product that is formed. So every time when the alkali metals or other reactive metals react with water, we produce a solution of their hydroxide, an alkaline solution, to mean that the solution is basic. You remember the bases and acids. And we also produce hydrogen gas. Generally, the equation can be represented like this. We have M in the solid state, which stands for a metal of group 1 elements. That can be lithium, it can be sodium, potassium, reacting with water, which is in liquid state. And then we go to the product side where we produce MOH in aqueous solution. That is the metal hydroxide with hydrogen gas. And here we have the example. Sodium in the solid state can react with water in the liquid state to produce sodium hydroxide in the aqueous state plus hydrogen gas. Now let's have some more examples. We have potassium reacting with H2O in the liquid state. What will be the product? We have sodium here. That is the example we have used. I'm writing it again so that we can get it balanced. We also have lithium in the solid state reacting with water. What will be the product? And you can also use rubidium. Remember, as we move down the group, the reaction becomes more and more vigorous and more dangerous. So when we complete this, we said we produce sodium hydroxide. It is a soluble compound, so it will be in an aqueous state, plus hydrogen gas. Is our equation balanced? You should always remember to balance the equations. And you should always remember to write the state symbols. We know which substances are gaseous at room temperature, which substances are soluble, which ones are insoluble, which ones are solid at room temperature, liquid. So never forget to include the state symbols in your equations, and you balance them. We have one sodium atom, and here we have one sodium. So the number of sodium atoms is the same on both sides. For hydrogen atoms, we have 3, 2, and 3, and here we have 2. So we can use a half mole of hydrogen gas. And then here we have a half mole and one hydrogen, then it will be 2. And we have one oxygen atom. The equation is balanced. Now let me give you some seconds, and you complete and balance those 3 other equations. Try it, please. We know that practice makes perfect. You remember that? Good. So hurry up. 3 equations. It's very simple. It's just like you have a model here, that of sodium. So you can do that in some seconds, like 30 seconds. 10 seconds for one equation, 10 seconds for one equation, and 10 seconds for the next and the last. Okay, it's time, so we go to potassium. What do we produce? We said that when these elements react with water, we produce soluble hydroxide, that will be potassium hydroxide, plus H2 gas, hydrogen gas. So we can put 2 here, and 2 here, and 2, so that we can produce 1 mole if we don't want to use a half. So here it is balanced. For lithium, what do we get? We get lithium hydroxide, which is also soluble, and we produce hydrogen gas, which is a half mole. Rubidium OH aqueous plus H2 gas, and as we did for the first one, you can put 2 here and 2 to produce 1 mole of hydrogen gas. Okay? Now, going back to our slide, it is said all elements react explosively with water. And the vigor of reaction increases as you move down the group. What does it mean? We have seen that. From the video I showed you in the previous lesson, you've seen that lithium reacts with water, yes, but less vigorously compared to sodium. If you remember well, sodium exploded. And if we go to rubidium and cesium, you have seen that cesium can even break a bathtub. Why? Because of the reaction being so violent and vigorous because, as we know, reactivity increases down the group. So we should be very careful when we are dealing with these reactions because they are very dangerous and they may be very explosive and cause a number of accidents. So it's very good if you be very careful with these reactions when you want to carry them out. Next, these elements react with oxygen. I hope you remember that. You remember the flame test or the flame color I showed you by burning sodium. Do you remember the yellow flame of sodium when it burns? And the white, very bright flame of magnesium. So these elements, either the group 1 elements or group 2 elements, but today we are focusing on group 1 elements, they react with oxygen to produce different types of oxides. So here I will tell you that we have 3 types of oxides, mainly. We have, and that will be another way of classifying the oxides because normally you know a classification which gives the acidic oxides, basic oxides, amphoteric oxides, and neutral oxides. But today, we will base on the molecular formula and the type of the oxygen ion which is present in the compound. So the metals, alkali metals, burn in oxygen to produce oxides. We have M2O. M2O, you can see in this case, because the charge of these group 1 metals is always 1 positive. So when we have M2O, we mean that oxygen has a 2 negative charge, O2 negative. And with this ion, we call them the normal oxides. Normal oxides. Normal oxides. And we also have peroxides. With peroxides, you can see that we have M2O2. And remember, the charge of M is always 1 positive because we are in group number 1. So if we have M2O2, it means that we have 2 positive on this part and we have 2 negative on this part. So the ion we have here is 2 negative for 2 oxygen, and we call these ones peroxides. Do you remember hydrogen peroxide? H2O2, hydrogen peroxide. It's the same. So we can also produce peroxides. And it is also possible to produce another type of oxides we call the superoxides with MO2. And in this MO2, the charge, remember, it is 1 positive, and because of that, the oxygen molecule will have a charge of 1 negative. And we call this one the superoxide. Whether a metal will form an oxide, a normal oxide, a peroxide, or a superoxide will all depend on the size. And because of that, if, for example, you make sodium react with oxygen, you produce 2 types of oxides. You can produce a normal oxide with the molecular formula general M2O, that is Na2O, okay? And you can also produce sodium peroxide because of its large size. But do you think lithium will produce a peroxide? It's not very easy because of the small size of lithium. So as the size increases, you can produce peroxides and superoxides. So potassium can produce a superoxide, but it's not very easy for sodium to form a superoxide because of its smaller size compared to potassium. So lithium forms a normal oxide only because of its small size. Here we said only, but it's not actually only, mainly. Let's say mainly, because of its small size. Sodium doesn't form superoxide because of the same reason, because of its small size. Here we have two substances. The substance which is pale yellow, and this one is yellow. This is sodium peroxide, this one, the yellowish white, and we have potassium superoxide, it is this one. Potassium superoxide is the principal product formed when potassium metal burns in air. Why? Because of its large size. The oxygen and water, they are not the only substances which react with alkali metals. We have other substances which can react with them. And here we have the reaction with the halogens. You know the halogens, those nonmetals in group 7, okay? So halogens can react with alkali metals, and as we have seen, that the reactivity increases down the group in the nonmetals, sorry, in the metals, the reactivity with the halogens will also be different because reactivity of the halogens also changes as you move down the group. We know that in the nonmetals, reactivity decreases as we go down the group. So when you take sodium and react it with fluorine, the reaction will be very dangerous. Actually, all reactions of fluorine are very dangerous. But the reaction will be not very violent if you use bromine, for example. So the reactivity decreases down the group in the halogens. And what do we produce? We produce salts we call the halides. M, that is the metal, when it reacts with X, let's say in the gaseous state, X stands for the halogen. Remember, they exist as diatomic molecules. We produce MX, this is a salt, in the solid state, and we put 2 here to balance. Okay? So the substances we produce, they are called halides, and they are salts, ionic compounds, because we have a metal combined with a nonmetal. So we can have sodium fluoride, sodium chloride, sodium bromide. You can have potassium fluoride, potassium chloride, and so on. They also react with hydrogen. And what do we produce when they react with hydrogen? They react with hydrogen to produce substances we call hydrides. And here there is something very important you should know. M reacting with hydrogen, which is a gas, at a high temperature, we have to heat, you produce MH in the solid state, and we balance, here we balance. And remember, electronegativity. The electronegativity, hydrogen is more electronegative than these alkali metals. So in these compounds, hydrogen has a negative charge. So it is M1 positive and H1 negative. And this ion is called the hydride ion. Hydride. And that is the reason why we call them metal hydrides. The compounds we produce, they are called hydrides. Okay? The alkali metals react with hydrogen at that high temperature, relatively high, to form metal hydrides with this general molecular formula, MH, where M stands for the alkali metals. So we have 2M in the solid state reacting with hydrogen in the gaseous state to produce 2MH in the solid state. These hydrides, they are also ionic compounds. Being ionic, they will be solids at room temperature and pressure. And here it is said the hydrides are basic. What does it mean? The hydrides are basic. Let's try this sodium reacting with hydrogen. What will be produced? What will be produced? Complete that equation. You have your notebooks or the exercise book, you have your pen, complete that equation. And then we will use the same equation or the product we will get to analyze the behavior, the acid-base character of these hydrides. Let me hope that you're done. We said that they produce hydrides, and it is MH, the general molecular formula. M here stands for sodium, so we have sodium hydride, which is solid, and we put 2 and 2. And then it is said sodium hydride, or these hydrides generally, they are basic in nature. How can we show that? When they react with water, what do we get? Reacting with water, we produce alkaline solutions, solutions containing a hydroxide. So we have sodium hydride reacting with water, we produce a hydroxide and hydrogen gas. Can you try and complete that equation? Sodium hydride reacting with water to produce sodium hydroxide. Let me tell you the name. There is no problem. You will write the molecular formula, and it is produced with hydrogen gas. Complete it. Here we have the general formula you can use, or the general equation you can use. You can refer to this one and complete it. And what we get sodium hydroxide, which is soluble, plus hydrogen gas. Is our equation balanced? Let's check. 2 hydrogen atoms plus 1, that is 3. We have 3. 1 oxygen atom, 1. 1 sodium, 1. Balanced. Good. Can we go to the next slide? Ready? Okay. They can also react with acids, but you have to be very careful with this. Acids are very reactive. And these metals are also very reactive. Now imagine what will happen when you take an acid and react. I hope you remember what happened when we are reacting sodium with water. You have seen that in the video. The reactions are very dangerous. Now imagine when we use acids. More and more dangerous. It's like you can make a bomb with a simple reaction of cesium, for example, with water. Now imagine if you take the same cesium and react it with concentrated sulfuric acid, for example, or hydrochloric acid. You can demolish a big house by simply using that. It's very explosive, I'm telling you. So we have to be very careful with this. And the reaction will be less violent if you use a dilute acid, of course. So they react with dilute acids to produce hydrogen gas and a salt. The single displacement reaction, here we have M reacting with aqueous sulfuric acid to produce a metal sulfate and hydrogen gas. So if we use like lithium reacting with H2SO4 aqueous, what will be the product? I said we produce a metal sulfate. Metal sulfate, you can combine this M with the sulfate, but here I've written it in the ionic form because the sulfates are soluble in water. But if you want, you can combine the two parts and you put there the state symbol. It is in the aqueous state. And we also produce hydrogen gas. So you complete this equation, please, and make sure it is balanced. Some seconds. It's very simple. Good. So we have lithium reacting. We produce lithium 2SO4 in aqueous state plus hydrogen gas. Hydrogen gas is our equation balanced. No, we need 2 here. And it's balanced. So these are some of the reactions. We cannot exhaust all of the reactions, but these are the common reactions. We go to the next, compounds of alkali metals. It is the first part. We have some compounds like the oxides and the hydroxides. Let's start with the oxides. Alkali metals form basic oxides. You know, mostly metal oxides are basic. So being basic, you can deduce what will be their chemical properties. They can react with acids. When they react with water, they will produce basic solutions. So alkali metals, they form basic oxides. They react with water to produce hydroxides. It's this one. They react with acids to produce salts and water. We know all of these reactions. So your work here will be to take the oxides and replace this M with any metal of your choice, and you try to complete the equations. The peroxides will always produce a hydroxide with hydrogen peroxide. And we said they can react with acidic oxides. Here we have the example, and you produce salts. And here it is very important to say that we cannot predict the solubility of these oxides. Why? Because they react with water. They react with water. And the hydroxides, they are basic. We know the behaviors of basic hydroxides, or the hydroxides in general. They react with acids. They can precipitate metal cations. We will do this, all of this, in a practical. It will be easier to understand. And the hydroxides can also react with acidic oxides. The solubility will increase down the group. We will also have a look at that with a lesson which is more practical than theoretical. And if we are saying that they become more soluble as we move down the group, then their basicity also increases as we move down the group. Now let us have a look at the homework you have. We have 1, 2, 3, 4 equations to complete. Sodium hydroxide reacting with iron sulfate, potassium reacting with water, lithium reacting with oxygen, sodium with HCl. And the last question, you will use the reaction of water to explain how the reactivity of these metals varies moving down the group. Thank you very much. See you next time.